Machine learning uncovers hidden earthquakes in Yellowstone, what it means for volcano safety. Unveiling the secrets of Yellowstone, machine learning sheds light on historical seismic activity. Yellowstone National Park, renowned for its breathtaking landscapes and the inspiration behind a beloved television series, holds the distinction of being the very first national park established in the United States. Beneath its surface lies one of the planet's most active volcanic systems, characterized by frequent seismic activity. In a groundbreaking study published on July 18 in the prestigious journal Science Advances, Professor Bing Li from Western University, along with his team from the Industrial University of Santander in Colombia and the United States Geological Survey, harnessed the power of machine learning to delve into historical earthquake data from the Yellowstone caldera, covering a span of 15 years. This innovative approach enabled the researchers to identify and assign magnitudes to nearly 10 times more seismic events than had been documented previously. A caldera, such as the one found in Yellowstone, which extends across parts of Wyoming, Idaho, and Montana, is a vast depression formed when a volcano erupts and the magma chamber beneath it is emptied, resulting in the collapse of the land above. This process is distinct from the formation of a volcanic crater, which occurs due to explosive outward eruptions. The updated historical catalog for the Yellowstone caldera now boasts an impressive total of 86,276 recorded earthquakes from 2008 to 2022. This significant enhancement in data collection and systematic analysis has greatly enriched our understanding of volcanic and seismic systems. One of the most intriguing discoveries from this research is that over half of the earthquakes detected in Yellowstone were part of what are known as earthquake swarms. These swarms consist of clusters of small, interconnected earthquakes that occur in a limited area over a short time frame, differing from aftershocks, which are smaller quakes that follow a larger main shock in the same vicinity. The Grand Prismatic Hot Spring, a stunning feature of Yellowstone National Park, is fed by a magma chamber located beneath it. The vibrant colors of the spring are a result of hydrophilic bacteria thriving in the mineral-rich waters. While each volcano, including Yellowstone, has its own unique characteristics, we hope that the insights gained from this study can be applied to other regions as well, stated Li, who specializes in fluid-induced earthquakes and rock mechanics. By comprehending seismic patterns, such as those seen in earthquake swarms, we can enhance safety protocols, better educate the public about potential hazards, and even steer geothermal energy projects away from risky areas with promising heat flow. Revolutionizing earthquake detection. Before the advent of machine learning, the detection of earthquakes relied heavily on manual analysis by trained professionals. This traditional method is not only time-consuming and costly, but also tends to miss many seismic events compared to machine learning techniques. This has led to a surge in data mining efforts in recent years. As seismologists revisit the vast archives of historical waveform data stored in global data centers to uncover insights about both current and previously unknown seismic zones. If we had to rely on the old-fashioned method of manually sifting through all this data to find earthquakes, it would be impossible. The process simply isn't scalable, Li explained. The research also indicates that the earthquake swarms beneath the Yellowstone caldera are associated with relatively immature and rough fault structures, in contrast to the more established fault systems typically observed in areas like Southern California and even just outside the caldera. The roughness of these fault structures was assessed by analyzing earthquakes as fractals, geometric shapes that display self-similarity across different scales. First introduced by Benoit Mandelbrot in 1980, fractal patterns can be observed in various natural phenomena, including coastlines, snowflakes, broccoli, and the branching of blood vessels. The fractal-based models used in this study, which focused on roughness versus regularity, successfully characterized these earthquake swarms, which the researchers believe are influenced by a combination of slowly moving underground water and sudden fluid bursts. To a large extent, we lack a systematic understanding of how one earthquake can trigger another within a swarm. We can only measure the spatial and temporal relationships between events indirectly, Lee noted. However, with our newly expanded catalog of seismic activity beneath the Yellowstone caldera, we can now apply statistical methods to quantify and identify new swarms that have previously gone unnoticed, allowing us to study them and glean valuable insights. What do you think? This research opens up a fascinating dialogue about the implications of machine learning in understanding seismic activity. Could this technology revolutionize how we predict and respond to earthquakes? What are your thoughts on the potential risks and benefits of geothermal energy development in seismically active areas? Share your opinions in the comments below. How AI is uncovering thousands of hidden small earthquakes in Yellowstone. Imagine a world where the subtle tremors of the Earth, often overlooked, hold the key to understanding our planet's geological mysteries. Small earthquakes, while typically unnoticed by the general public, occur far more frequently than their larger counterparts. Gaining insights into these minor seismic events can significantly enhance our comprehension of earthquake risks and the geological dynamics at play in specific regions. However, measuring the magnitude of these small earthquakes in Yellowstone National Park presents its own set of challenges. This is where the innovative application of artificial intelligence, AI, comes into play, offering promising solutions to these complex problems. In Yellowstone, the University of Utah Seismograph Stations, UUSS, operates a sophisticated network of seismometers designed to monitor seismic activity. Earthquake magnitudes are determined based on the energy released during these events, as recorded by these instruments. Typically, multiple stations within the network independently measure the magnitude of a single earthquake, and these individual estimates are averaged to produce a final reported magnitude. However, accurately calculating the magnitude of small earthquakes can be problematic, particularly when there are insufficient measurements or when multiple earthquakes occur in close succession. This issue is especially pronounced during swarms of small earthquakes, where the signals from individual events can overlap, complicating the analysis. While seismic analysts can often resolve these overlapping signals after locating the earthquakes, this is not always feasible. In fact, approximately 2% of the earthquakes cataloged by UUSS lack a computed magnitude, often due to these overlapping signals, resulting in a placeholder value of -9.99. To address this challenge, we can turn to the powerful tools offered by AI. Many people are familiar with advanced deep learning models such as ChatGPT, which can process and generate complex data, including lengthy text and images. The deep learning models employed in analyzing small earthquakes operate on a similar principle, utilizing ground motion data from seismometers as their input. These models are a subset of machine learning, which encompasses algorithms that identify patterns within datasets to predict values for new data. During the training phase, the model is exposed to numerous examples, akin to taking a test with an answer key. Once trained, the model can process new inputs it has never encountered before and generate estimates based on its learned patterns. Additionally, there exists a more straightforward yet still effective type of machine learning that relies on human-defined features to describe the data, rather than using raw data directly for predictions. In a recent study, scientists at UUSS employed this method to train models capable of calculating earthquake magnitudes based on short data windows, effectively mitigating issues that arise when earthquakes occur in close proximity. In this innovative approach, UUSS scientists developed a separate machine learning model for each station within the Yellowstone region, utilizing data from the USS Earthquake Catalog. Each model incorporates features that describe the earthquake signal, such as amplitude, and the earthquake's location to estimate its magnitude. This new methodology optimizes the use of available data by considering various types of seismic waves and leveraging information from multiple seismic stations, thanks to the thorough training process. As a result, the number of measurements available for calculating a magnitude can increase by up to 4 times. Similar to traditional methods, these measurements are then combined to determine a final magnitude. It's important to note that this new approach is intended to complement, rather than replace, conventional methods for calculating magnitudes. Traditional techniques are generally effective, except in cases involving small, closely occurring events. Moreover, the machine learning models have their limitations. They perform best when applied to earthquakes that resemble those in the training dataset. For instance, if a model has limited training examples from a specific area, such as near Hebgen Lake, it may struggle to accurately estimate the magnitude of an earthquake in that region. Likewise, if the majority of training examples are for earthquakes greater than magnitude 0.5, the model may not perform well for smaller events. By combining predictions from multiple station models, we can identify and eliminate poor magnitude estimates, although determining when the models are uncertain can be challenging. Looking ahead, UUSS scientists aim to enhance this approach not only to provide magnitude estimates, but also to assess the confidence level associated with those estimates. These machine learning techniques represent the forefront of seismological research, and Yellowstone serves as an ideal testing ground for these cutting-edge methods. The Yellowstone Caldera Chronicles is a weekly column authored by scientists and collaborators from the Yellowstone Volcano Observatory. Feel free to share our stories online or in print under the Creative Commons license CC by NCND 4.0. We kindly request that you edit only for style or brevity, provide appropriate attribution, and link back to our website. Please note that AP and Getty images are not permitted for republication. For guidelines on using other photos and graphics, please refer to our republishing guidelines. Yellowstone's hidden quakes. AI reveals 10 times more earthquakes than we knew. Prepare to be amazed. Yellowstone is shaking far more than scientists ever realized, by a factor of 10. Just when we thought we understood the seismic temperament of this legendary supervolcano, a new study has shattered expectations. But here's where it gets truly fascinating. Modern machine learning technology has just exposed over 86,000 earthquakes within Yellowstone's caldera between 2008 and 2022. That's about 10 times the number previously detected. How did researchers unearth so many previously hidden quakes? A collaborative team from Western University, Universidad Industrial de Santander, and the U.S. Geological Survey harnessed powerful algorithms and cutting-edge AI. By meticulously analyzing 15 years of seismic data, something impossible to do by hand, they reconstructed Yellowstone's earthquake history in extraordinary detail. The results were unveiled in Science Advances on July 18, 2025, marking a huge leap in volcanic research. Let's break it down for those who aren't seismologists. The Yellowstone caldera is a vast, bowl-shaped volcanic depression sprawling across parts of Wyoming, Idaho, and Montana. Underneath it all lies a churning magma chamber, feeding wonders like the Grand Prismatic Spring with its dazzling rainbow colors created by bacteria thriving in its mineral-rich waters. Historically, tracking earthquakes here depended on manual review and older, less sensitive algorithms, making it easy to miss the smallest or overlapping events, especially during intense earthquake swarms. In a bold move, scientists equipped each monitoring station in Yellowstone's dense network with its very own AI model. The result? Better magnitude assignments, even when quakes happen one atop another. In a striking example, the algorithm found 855 new earthquakes within just a 10-day swath of data and confirmed over 99% as genuine events. But, and this is the part most people miss, more than half of these tremors didn't act like classic solitary main shock aftershock sequences. Instead, they occurred in dense clusters or swarms, dozens or even hundreds of small quakes fanning out through immature, rough fault lines. not through well-established earthquake zones like you'd see in Southern California. Think of these as rocky, incomplete cracks rather than smooth, time-worn fault scars. Researchers even quantified this fault roughness using fractal geometry, an advanced way of measuring the irregular shapes and patterns formed by these seismic clusters. So what's causing these quirky swarms? The evidence points to a complex interplay of slow-moving underground fluids and abrupt pressure changes in Yellowstone's vast hydrothermal system. These processes, scientists suggest, nudge and jostle the developing fractures running beneath the caldera. Notably, fault segments there were much rougher than those further away, a hint that Yellowstone's underbelly is in a state of constant active rearrangement. And here's a new twist worth debating. To tie all this together, researchers built a detailed, three-dimensional model of how seismic waves move through Yellowstone's crust. This breakthrough allowed far more accurate pinpointing of earthquake locations and sizes, taking into account all the underground lumps and bumps that distort seismic signals. Many experts believe these findings could reshape how other volcanic areas are monitored, making geothermal power development both safer and more efficient. As Bing Li, the study's lead author, points out, by unraveling seismic patterns, especially elusive swarms, we can empower communities and guide essential safety protocols. We might even steer geothermal projects away from the riskiest spots, all while tapping Yellowstone's massive energy potential. But the study invites plenty of debate. Could this unprecedented earthquake count signal mounting volcanic pressure? Or is it just a testament to new technology sensitivity? Should geothermal energy projects proceed in regions with such dynamic seismicity? Are we finally seeing Yellowstone's full seismic picture? Or are there surprises yet to come? What do you think? Does this avalanche of new quakes concern you? Or reinforce your faith in science's capacity to keep communities safe? Where do you stand on the use of AI and 3D modeling in predicting volcanic risk? Share your perspective or counterpoints in the comments. This is one story that's sure to spark discussion.